My name is Roberto Garcia. I'm with the Analytical Instrumentation Facility, and I'm in charge of the FIB lab. And with me and the speaker today is Nicole Cates. So Nicole has been in the lab for quite some time, and she is probably the expert right now when it comes to patterning. So I'm gonna let her, and she's at a really cool company that's doing some really neat stuff. So I'm gonna let her introduce herself and talk a little bit about the company and then get started. So I'm gonna mute myself and then turn it over to her.
All right, we should be good now. I'm gonna turn on my speaker. Feel free to jump in and ask questions along the way, or put questions in the chat. I'll try to answer them as we go, especially since it's a smaller group. Yeah, it's a great opportunity to just have some discussions along the way. But as Roberto said, my name is Nikki Cates. I work at a small company called Smart Material Solutions. We spun out of NC State, I guess like 6 years ago now, which is crazy. But we do large area nanopatterning. Our process involves first nanopatterning diamond and then stamping that diamond that is nanopatterned into a metal, and thereby copying whatever pattern we made in the diamond into the metal. And the key is that we do that extremely quickly, and we do it around a cylinder, so we can cover the outside of a cylinder with some type of nanopattern that we've made with traditional techniques, but we can do that extremely quickly. For those of you that care, we can do that about 1 to 2 square inches per minute seamlessly around a cylinder. But today's lecture is not on that. It's on our first step of our process, which is nanopatterning with a FIB. I'm specifically going to be talking about nanopatterning diamond, because that is what we generally use, since diamond is such a hard material and it can be used to indent into metal for our process. But 95% of what I'm going to say today is not specific to diamond. It can be used to nanopattern any material. So if you're looking to pattern silicon, for example, you can use the processes I'm talking about. We have also used the processes to nanopattern a variety of materials: sapphire, gallium nitride, silicon, a couple of things. We tend to stick with diamond for our process, but as I said, it's very flexible. So I'm going to share my screen, which is some slides. Actually, I'll share the whole screen, because I might later want to share some other stuff. But we'll start with these slides. And I'll go through kind of the theory behind what we're doing to nanopattern with a focused ion beam. But then we'll shift into a demonstration, and that will be on the Quanta. I guess it's Thermo Fisher now. It used to be FEI at NC State, and that's a gallium FIB SEM dual beam system. So we'll talk about that, show you some examples of how to actually use the equipment at NC State after we first talk about the theory. So FIB nanopatterning. There's a couple of different methods to nanopattern with FIB, and I do want to talk a little bit about all of them. These can be broken down into 2 categories. So that's FIB nanodeposition and FIB nanomachining. I show a great example. This is from literature. I cannot take credit for it. It's from FIB Incorporated. But I think it's a great demonstration. If you're nanodeposition, you're depositing material, adding material to something that's already there, and you're doing it with nanoscale precision. If you're machining, you're removing material. I tend to do machining, but we have done a little bit of nanodeposition, and other people have done a lot of nanodeposition and done really cool things with it. So we'll talk about that first, and then we'll switch into nanomachining. So nanodeposition is usually done with a process called ion beam induced deposition, or IBID. The general idea is that you use a precursor that is inserted into the microscope's chamber, usually with a needle. This can be done at the NC State one, for example, with platinum. So you introduce the precursors for platinum or whatever you're trying to deposit, and then you use either the electron beam or the ion beam to cause a reaction of those precursors, and that causes the deposition of a material wherever you put the beam. Wherever you don't put the beam, this reaction is not caused, and you don't deposit the material. So by doing this and controlling where your electron or your ion beam is, you can control where you deposit things on the nanoscale, which is pretty darn cool. You can also use this to selectively expose resist that you've already put down. That's another process that I believe at least one of you guys have done before, from what Roberta says. So people have done some pretty cool things. This is an example. Again, not my work, but someone has made this stick figure. And one cool thing you can do with this IBID technique is build something from the ground up, kind of like you can do with 3D printing. It's just on the nanoscale. So you can build something that, you know, has 3 dimensions, like this. I guess this guy's like 2D, but he's standing up. But you can also do things that are 3D. And I'll show you some examples in a second. And you see, it does take some time, but if you change where you're depositing your material, you can create 3D structures. Here's some other examples of things that other people have done. Made a fake little virus, the Leaning Tower of Pisa, and my personal favorite, the Star Trek Enterprise. So yeah, people have done some pretty cool stuff with IBID. Now I'm going to switch gears. If anyone has any questions about IBID, I'd be happy to try to answer them. I'm definitely not an expert there, but if no one jumps in and asks the question, I'm going to keep going. So I'm switching over now to FIB milling or FIB machining. This is what I traditionally think about when I'm thinking about FIB nanopatterning, but maybe that's just because this is what I normally do. So the idea with FIB machining is you're using an ion beam to remove material using sputtering. So I want to break down this diagram here. What you have here is a gallium beam that's being focused onto a gold sample. The gallium ions come in, and it has a couple of things it can do. It can become implanted inside of your gold, or whatever your substrate is that you're milling away. It can also cause a collision with these atoms and knock off the gold atoms. So you see, it says here gold sputtering, so you can cause the gold atoms to sputter away. You can also cause the emission of secondary electrons. And another process that's important, and we'll talk a little bit about, is called redeposition. And that's where your gallium or whatever your ion is comes in, it knocks off an atom of your substrate that gets sputtered away, but then it kind of flies away and then reattaches to your substrate at a different place. And that's called redeposition. And that is something that we definitely have to think about as we're doing FIB machining. So we'll talk a little bit about some of the implications of redeposition and how it affects things in a minute. So before we jump into the specifics, I just wanted to show you some of the cool things that can be done. These are examples of things we have FIB milled. Actually, either myself or my colleague, Lauren Miklo, have FIB milled at the AIF with AIF equipment. So we've done some nano features. These features are about 250 nanometers center to center distance. So we can do nano features actually to under 100 microns, under 100 nanometers center to center distance. So you can go pretty small. You can also do nice micro features. This is an example of a microlens array we made for a company. We can do hierarchical features where we have nano features on type of micro features, and these can have really interesting optical properties because they combine the optical effects of these nano features with something like a microlens array. We can do things like pyramids, linear gratings, done some stochastic features where it's a little more random. And we've also done some arbitrary features. So this is an example of us. We made our logo, our company logo, in diamond. And we actually then used our process to replicate this into the outside of a cylinder. So we literally made billions of copies of our company logo, which was just a fun little experiment. And recently, just to show you more arbitrary features, I milled mine and my fiance's name into the side of my engagement ring because I have a diamond on my engagement ring, so I decided to write our names on the side of it. So you can do a lot of random cool things with focused ion beam milling, and all of this, as I said, was done at the AIF at NC State. All right, so when we're thinking about FIB milling, one of the big things we have to think about is the shape of the ion beam. Because when you're doing, say, traditional milling in a machine shop, you're only milling away at the point where your drill bit is, or your milling bit is. However, if you are milling with an ion beam, it's a little different. So if you're focused, say, at the point where this X is, you're definitely milling at that point. But the beam has like a Gaussian shape. And as a result, you're milling a little farther away, and a little bit even farther away, because you have these beam tails that keep going. So you have to take that into account. If you're milling a single point, you're actually milling a little bit all around that point. And you can see that this is an example where you cut a slice in a material, and you can see that the cross section has this shape of somewhat a Gaussian beam. So this is very important to remember when milling a feature. If you have a sharp side to a feature you're trying to mill, chances are that side's going to be rounded a little bit. Whereas with traditional lithography and etch and lift-off processes, you can get very sharp edges to your features, very sharp sidewalls. That is actually extremely difficult to do with the ion beam because you have this beam shape. So I think it's actually an advantage in a way if you learn to work with it, but it's something that you have to keep in mind, that there's this beam shape and it's going to affect what your features look like. Another thing that's really important to remember when you are doing patterning with a focused ion beam is that there's an angle dependence to the sputtering rate. And I'll explain a little bit what that means, but here is a plot of sputter yield versus incidence angle. And you see that the sputter yield, which is the atoms you get sputtered per ion coming in, that changes dramatically versus angle. So I want to show you what that means. On the left side, at an incidence angle of 0, we have our ion beam perpendicular to our surface that we're trying to sputter. And that means that whenever you're trying to sputter, the gallium ion has to come in and kind of like bounce off to the side, and you have to cause these atoms that you're trying to sputter to bounce off to the side to get good milling. Which, as you can imagine, since it involves knocking things off in the opposite direction as the incoming ion, that's not a particularly efficient process, which is why the sputter yield is so low. But if you go to, say, 80-degree incidence angle, you look something like this. And now it's much easier for the incoming ion to sputter atoms away because you have this more ideal directionality going on. And this can have huge implications for how we mill features because, you know, something that is milled at a tilt angle is going to mill, in this case, you know, 8-9 times faster than something that is milled at a normal incidence. And you may think, oh, this doesn't matter. I'm always going to have my sample at normal incidence, which is what I normally do. But it can matter quite a bit. So I want you to consider the case where you have a feature like this. You've already made this feature and you want to fine tune the feature. Well, in the center of the feature, you have an incidence angle of 0. So you have a very low sputtering rate. At the edge of this feature, you have a very high incidence angle, so you're going to have a very high sputtering rate. So if you were to evenly mill this entire feature, rather than making the entire feature a little bit shorter, you would actually make the feature a little bit skinnier, because you would cause milling to happen very quickly on the outside here, while it's happening much more slowly on the inside. And as a result, I often get asked like, oh, I want to make a perfect parabolic feature. How do I do that? Can I just make a bitmap that makes the milling occur like a perfect parabola? And the answer is unfortunately not. It's not that simple, because there is this angle dependent sputtering rate that definitely causes some complications. So yeah, definitely this is worth considering when you're thinking about how to mill a specifically shaped feature. Another thing to consider is redeposition, which I mentioned earlier. So as I said before, redeposition is when you have material that you've sputtered away that redeposits onto your substrate. So you can imagine as you're making a trench, for example, as you see on the left here, the deeper you make the trench, the more you have material redepositing inside of that trench. So in this case, you may be trying to make a wide trench, but you keep redepositing and filling in your trench. Definitely something to consider, and I'll show you some ways to get around this as well in a minute. Also, if you're fibbing, say, from one side of the feature to the other side, as you're fibbing near the end, remember that you're constantly redepositing. And in this case, you're actually, say you're fibbing here. You're redepositing on the left and on the right, but then you're moving the beam to the right. So you're removing the material you redeposited on the right, but not removing it on the left. So a lot of times it's therefore important to understand where the beam is going, how many times it's going over a particular surface, and in what direction it's going, so that you understand if redeposition is going to be an issue. And to give a great example from literature, this is the same feature created with two different processes. So in the left here, they milled this Y shape in this material, and they did a single pass with 882 microseconds of dwell time, meaning that each point, the beam stayed for 882 microseconds before moving on. And you can see that there's a substantial amount of redeposition, and that's evidenced by the kind of distortion of the shape. You can see that, you know, even though they tried to make a trench, it's, you know, doesn't have a flat bottom. It's got this tilted bottom, and that's because of redeposition. Now, if instead of doing a single pass at 882 microseconds, they do 882 microseconds where there is, or sorry, 882 passes where there is 1 microsecond dwell time. So they did 1 microsecond here, and then 1 microsecond here, and 1 microsecond here, and they did the entire pattern, and then they repeated it 882 times. You see that you get a completely different result. And that's because even though there was redeposition on this right side, with each subsequent pass, we were able to better remove the redeposited material. And therefore, redeposition doesn't appear to be as big of an issue, because you didn't allow like the snowdrift essentially to build up each time, because each pass you're knocking off whatever was redeposited before. So there are certainly reasons to do a single pass, but they are special cases. And for that reason, I generally recommend doing many passes when we're doing a patterning process. And I'll show you some of that when we get to the actual hands-on demonstration part. So another thing to consider about redeposition is your beam path. So say you want to make these circles, these holes in your material. You have a couple different options. You can do a raster scan, meaning you're always, in this case, going right to left, right to left, right to left. I know that our FIBs also allow a serpentine, which is right to left to right, right to left to right, and like a snake pattern across. But you can also do a spiral scan. Now, this isn't something that is built into many FIBs, but there is a process by which you can control exactly where the beam goes. And by doing this, you could make a spiral that, as you can imagine, is going to make redeposition more circularly symmetric. Whereas in this case, if you're always going right to left, you're always going to have redeposition that's causing your features to be lopsided. And I'll show you the SEM cross sections of these two examples. So here on the left is the scan that's always doing the raster scan right to left. And you see that there is redeposition on the right side here because we always have that directionality. On the right side, these features were milled so that each feature had a spiral, and you see that the features are much more symmetric. So again, it's important to understand not only how many passes you're taking when you're doing the milling, but also your beam path. And as I said, I'll talk about some ways to control your beam path in a minute. But before I do, I did want to talk briefly about the plasma FIB. I know many of you have probably used the plasma FIB here at NC State or another plasma FIB. So today I'm on the Quanta FIB here at NC State, and that is a gallium FIB. There's also something called a plasma FIB. So the gallium FIB has a liquid gallium source that is used to create the gallium ions. A plasma FIB has a plasma source, so it's like an ionized gas that is the source for the focused ion beam. Now, there are some advantages of the gallium FIB as well as some advantages of the plasma FIB, but a lot of it is captured in this graph that you see here. So this plots the image resolution versus the current, the FIB's current. So in orange, you see the gallium FIB, and you see that it has lower resolution, meaning it can get smaller features than the plasma FIB. But its current is limited. You see that this kind of tails off, and at some point, the gallium FIB crosses over and the resolution is no good, and turning up the current anymore is just not going to be useful for us. So this is where the plasma FIB really comes in and can make things a lot better. So we can keep turning up the plasma FIB higher and higher and higher current. And yes, we are losing a little bit of resolution, but by turning up the current, we're driving more and more ions at our substrate, which means we can sputter material faster and faster. So the plasma FIB has the ability to sputter much more quickly than the gallium FIB, although it's at the cost of image resolution. So if you want the highest resolution possible, you're probably still better off with the gallium FIB. And this table on the right shows a little more of some interesting stuff here. So this compares the xenon FIB, which is a plasma FIB, to a gallium FIB. And you see that the xenon is able to sputter more atoms per ion than the gallium. So it's already better at sputtering material. It has a higher sputtering rate per nanocoulomb in this case. And it has a much higher maximum current. So the end result is it can sputter material a lot faster than the gallium FIB. And I have a couple examples of materials that or comparisons where I've done the exact same thing on the gallium FIB and the plasma FIB. And I want to show you the difference. So as I said, the gallium FIB still is best if you want high resolution features. So for example, these are on the left, 300 nanometer features that I made on the gallium FIB. And you see that I have nice feature resolution here. No problem resolving the features. Everything looks good. On the right, I've used the oxygen FIB, which is one of the options for the plasma FIB at NC State. This is the best resolution I've gotten on the plasma FIB. And those are 1200 nanometer features. So these are 4 times larger than the features on the left, and still you can barely resolve them. So if you want very high resolution features, you're really better off using the gallium FIB. But if you want bigger features, the plasma FIB really shines. So here's what microfeatures look like in 3 different FIBs. The left being the gallium FIB. Then I have the oxygen plasma FIB and the xenon plasma FIB. Now, if I'm making these nice micro lenses and I care exactly what they look like, you'll see that the gallium FIB still has better resolution than either one of these other FIBs. But the difference is that the other FIBs are able to FIB dramatically faster. So on this top row here, I have about 50 nanoamps. In the case of the oxygen and the xenon FIB, it's 45 nanoamps, but these are all about the same current, about the same voltage. And we see already the oxygen and the xenon FIB are able to make these features dramatically faster than the gallium FIB. So this one took 106 seconds per feature, this one took 74, and this one took 74. Now, if I want to make a taller feature, I can crank up the current. So in this case, I've done 65 nanoamps, 190 nanoamps, and 65 nanoamps. These are super ugly. And I just kind of wanted to point out there that even though I've removed a lot of material here, choosing the right beam can also affect, or changing the beam can affect how these features form. I don't know why these are so ugly, but it's interesting that just changing from oxygen to xenon can dramatically change the features. But you see here, I'm able to crank up the current a ton. And because I can go to 190 nanoamps and still have some decent resolution, I'm able to make a feature in 93 seconds, whereas the same size feature took me 280 seconds with a gallium FIB. So that's a huge improvement in FIB time that you can get by switching to a plasma FIB. So whenever I need to remove a lot of material, I personally like to use the plasma FIB now, just because I'm able to do things so much more quickly. However, when I need high resolution, I still go back to the gallium FIB. All right, now I'm going to switch gears just a little bit because I wanted to mention all the cool ways to pattern with an ion beam. And one of these is called ion implantation masks. This is a really cool process. It works in diamond. This also works in silicon. And I know most of you are probably interested in silicon. So this definitely works in silicon. The idea is by using a focused ion beam to expose the material, we can implant gallium. And it turns out implanting that gallium can cause the material to be very resistant to etching. So then you can use, say, a reactive ion etch to remove material, and wherever you've exposed with the gallium will be protected. And this is really great because you don't need a high dose at all to expose and implant the gallium into your surface. And for that reason, you can pattern very large areas extremely quickly, and you don't even need a resist or anything because it's just a built-in hard mask. So we've used this a couple of times as a process to pattern. It does have to be used with the subsequent etch process, but it's a very fast patterning process. This I have tested does not work with the plasma FIB. So if you were to, say, do the same process with an oxygen FIB, it does not work. This is a gallium FIB specific thing, even though it does work with both diamond and silicon. And these are some examples, not of what we've done, but what a company called Adama has done with this process. So they, for example, exposed this checkerboard and then done an etch, and they can get these nice features. They've exposed their logo and etched, and again, you can get these nice features. I don't have any pictures here in this particular presentation but I have done this as well and been able to make some very large area nano patterns with features as small as about 200 nanometers center to center distance. And we've had a lot of success. And to do that, we've used the gallium FIB here at NC State in conjunction with reactive ion etching at the NNF at NC State. All right, so now I'm gonna switch a little bit into the hands-on parts, but before I switch over to the microscope, I wanna show you guys some of the things we're gonna be paying attention. So this is patterning specifically with an FEI or a Thermo Fisher FIB. A lot of this can be translated to other FIBs, but the specifics will be subtly different if you're using a different FIB. So for this, we have 4 screens. On the left here, this is the scanning electron microscope image. Then we have the focused ion beam image. This is just extra, and then we can see a camera to see inside of the chamber. So in this case, this is the surface of a diamond, and I'm looking straight down on the surface of the diamond with the focused ion beam. So this tab here on the right or the panel here on the right has all of these different options, and the third one here is the patterning option. So we'll talk about that in a minute. But basically, you can select different things. I often select bitmap, and I'll show you both what is called a bitmap and a stream file to control patterning. For a bitmap, you have several different inputs you can put, and I'm going to show you what some of those are. But basically, the size of your bitmap, how deep you want to scan it, your dwell time, which we talked about, how long the beam is going to sit at each position. And again, I'll show you that in a second. If you drop down on that menu, you'll see that there's several different options. Rectangle, many of you are probably familiar with cleaning cross-section or regular cross-section if you've done some TEM lift-outs. There's also circle, line, polygon. I tend to use bitmap or stream file, and I'll run through them both. So with a bitmap, you may start with something like this. It is a black and white bitmap, and what you do is essentially you input this into the microscope, and the microscope is going to scan its beam. It can actually scan the electron beam as well and do this, but I'm going to have it scan the ion beam because I want it to mill. So we'll scan the ion beam. Any point that is pure black, it will not hold the beam there for any amount of time. Anything that is pure white, it will hold there for the maximum amount of time, which is your dwell time. Anything in between that is gray, it will hold for whatever amount of gray it is. So if it's like perfectly in the middle gray, it will hold it there for half of the dwell time. And so by defining a black and white bitmap or a grayscale bitmap, you can define how much the beam sits at each position. Now remember that you don't have control with a bitmap with where the beam goes, other than to say, like, I want to do serpentine left to right or something like that. You can't say, I want you to do this feature, and then I want you to do this feature, and then I want you to do this feature. You don't have that type of control with a bitmap, but you do have control of how long it sits at each position. And I'll show you also have control of how many passes it does along the way. So whether you want it to do just one pass or to do 1,000 passes, you can control that. Now this particular bitmap here was used to create this pattern that you see on the right. And you see that because there is a beam tail, even though we're actually fibbing very little in these corners, there's nothing left in this corner. And that's because, you know, when you're fibbing, say this point, you're also fibbing in this corner. And so you end up with some rounding of the features. I'll also briefly talk about fibbing with a stream file. A stream file is a text file that you use to input that you input into the microscope, and it's going to tell the beam where to go and how long to sit at each point. So a stream file looks like this, although it's very, very long. So I've only shown like the first 10 lines here. I have a note here that it is not compatible with drift control, which is an FEI bug. I've spoken with engineers at Thermo Fisher many times, and although they swear that it's fixed, it doesn't work. So that is maybe a frustrating problem. I'll show you how to use drift control, but I have not been able to get drift control to work with stream files. Nevertheless, if you use a stream file, this first line just tells the computer that it's a 16-bit stream file. If you wanted to use a 12-bit file for some reason, you would just put S instead of S16. 1 is the number of passes. For a stream file, I actually like to use 1 pass because you're controlling exactly where the beam goes. However, you could make that 100, whatever. It's going to repeat whatever you have in your stream file, however many times you say there. The next is the number of points total in 1 pass. In this case, there's almost 50,000 points per pass, so that's a lot. And the next is a series of numbers. For each line, it is the dwell time in units of 0.1 microseconds, followed by the X position and the Y position, where the X and Y positions are essentially the pixel space. So you have to, when making a stream file, kind of input the magnification you're using, because I'll show you when you have a bitmap and you've defined that the bitmap is, say, 5 microns across and 5 microns tall. If you zoom in and out, it adjusts accordingly. Since a stream file is in pixels, you can zoom in and out and the stream file does not change its size. So that's important to know if you're trying to make features that are a particular size. But regardless, I usually use Python to make this because I don't want to make 50,000 points manually. But using a simple Python script, you can make whatever shape you want, and you can program the dwell time, the X and Y positions for each point. All right, so with that, I'm going to switch over to the other computer and show you a patterning demo. So I'll try to go through that again. Sorry about that. Basically, what I was saying is you upload your bitmap. It can be any bitmap. Here we've used a minion. You control your size, your X, Y, Z is the depth. Though it's important to know that unless this has been calibrated, and in this case it has not, the depth is not going to be accurate. So if I have 6.73 microns here, it is probably not going to be 6.73 microns deep. Just be aware of that. It's easy to calibrate if it matters. I have not calibrated it for this particular thing. And what I was saying is that there's an interplay between this depth in Z, your dwell time, and your number of passes. So if I have a dwell time of 1 microsecond, then here I have, well, 100 passes and only 0.07 microns. But let's say I make my depth 5 microns. I have a dwell time of 1 microsecond. Now I'm gonna have almost 7,500 passes. However, if I change the dwell time to 100 microseconds, it's gonna automatically change my number of passes to 1/100th of what it was before, so 74 passes now. So that's important to realize that if you're changing either the Z size or the depth, the dwell time, or the passes, they're all interrelated and things are gonna change. The other thing to notice is your total time here, which is the total time it will take to complete this process. So I guess since we have the minion up, I'll do a very quick one. I'm gonna say 1 microsecond. And we'll just do a much shorter depth because we don't want to be here forever. So I'm just starting 1 minute and 30 seconds. Hopefully we'll still be able to see this with our minion. While that's going, the next thing we're going to do is actually use a bitmap to make patterns. But you know, you can always do cool things like minions too, or whatever picture you care to do. I know that, I know that NC State did a thing on a librarian's strand of hair. They did like the logo of the library, I believe, something like that. So you can do some cool things with the patterning. So also what I said, I guess after we switched, is on the bottom here, we've got our sample. You'll see that it's tilted. And the reason it's tilted is it's tilted to face the ion beam. So the sample is normal to the ion beam, which is why on this screen, which is the focused ion beam, we're looking straight down. The electron beam is coming straight down on this image, like you see here, which is why the electron beam screen, which is on the left, is tilted. So yeah, just be aware that that's why this sample is tilted the way it is. All right, so when this is done, we'll stop this. We'll look at the image on the left. I'm not sure if we'll actually see a minion or not, but it'll be pretty cool if we do. So yeah, really any bitmap works. All right, there it goes. Okay, you can kind of make out the minion. It's not the greatest, but you know, he's there. So yeah, you can make whatever you want, minion or anything else. All right, so now I'm gonna switch over. I've deleted that pattern. I'm gonna make another bitmap, draw something, and I'm gonna pull in one of these bitmaps I've made. I'll make it bigger for a second so you can see it. This is similar to the bitmap I had in the presentation. You see that I have these circles that are white, so I'm gonna hold the beam there for the maximum amount of time. Anywhere you don't see anything in this image is pure black actually, so we're not gonna dwell any time in the center here. But this, even though it looks black in the corners between the features, is actually like very dark gray, which means there'll be a tiny bit of dwell time there. So I'm gonna go ahead and make this bitmap 5 microns by 5 microns. And if you looked closely, there were 5 features in the bitmap. So that's going to make 5 by 5 features. And I'm going to make the features 5 microns deep, but remember that doesn't actually make the features 5 microns deep because this has not been calibrated. And just because I'm looking at what I have done in the past with this particular bitmap, I'm doing 100 microseconds, which gives us 74 passes, which is a good number of passes. It's enough that I don't have to worry too much about redeposition. But it's not so many that it's like constantly restarting the scan. I don't know, I like around a couple hundred, like 800 to a couple hundred. You can do it where it's got 50,000 passes, but that seems unnecessary to me. All right, so I'm gonna turn this on, make sure it's nice and focused. It appears to be pretty good. This particular pattern is going to take us 1 minute and 6 seconds. So I'm going to go ahead and get that started. And you'll see that while we're doing it, it is scanning. As long as you don't have drift control on, you can actually watch it go in real time. So I'm currently changing the contrast so you can see that it is scanning each time and it's imaging everywhere that it's scanning across, which sometimes is nice as, you know, you're, doing something, you can get an idea, you can get some instant feedback. As I said, you can't see that I'm doing this, but I am manually changing the brightness and contrast, because otherwise, if I don't change anything, you can't actually see that it is scanning. But by manually changing this, you can see each scan. So you can get an idea that you're actually imaging, even though it looks like nothing's happening. All right, so when that finishes, we'll take a look at the electron image here, and we should see some features that appear. All right, so let's see. Ta-da! We have features. So that's what you can make in about a minute. Please focus a little better, looking a little nicer for you guys. All right, so these are the features that we just made. I'm not going to save that. I do want to talk about, choosing the right current for what you're doing. So right now, you'll see that I have a current of 3 nanoamps. You can see that in kind of the top left. It says 3500X, 30 kilovolts, and 3 nanoamps. I happen to know that 3 nanoamps is a pretty good current for these features, which are about 1 micron spacing, because I have 5 features in a total of 5 microns. Now, if I make my features too small for my current, I will end up just digging a hole because I don't have the resolution to do that. So to give you an example, instead of making these features 5 by 5, 5 microns by 5 microns, I'm going to make them 3 microns by 3 microns. And since there are 5 features, that comes out to be 600 nanometers per feature. I'm also going to change the depth to match, so it's going to decrease the amount of time it's going to take. And I'm going to go ahead and start this. But before it's even finished, I can tell you what we're going to see. We're going to see that we've just dug a big hole. And it's because I've tried to make too small of a feature for my beam size. So as a result, we're just digging a hole. We don't have the resolution we need to make features. It's like the same thing as if you were to look at teeny tiny features in an optical microscope. You don't have the resolution to do it. And so it just kind of mushes out. All right, so this is about finished. When it finishes, I'll show you the big hole we dug. All right, there we go. So we dug a hole. So if it's very possible to make 600 nanometer features, I would just need to turn down the current. You can see that I can change the current. Oh, well, this is the electron beam. Let me come over here. I can change the current. So I could lower the current to, say, I actually don't know exactly what I'd need to do, probably like 0.5 nanoamps about. And then I would be able to make beautiful 600 nanometer features. But I can't currently do that with the current I'm at. And on the other end, I want to show you if I make this much bigger. So let's say I make this 15 microns by 15 microns. And just so we're not here forever, I'm going to make this 10 microns deep. And so that's going to take us 2 minutes. And I'll go ahead and get this started. But what you'll see is, because the features I'm making are so much bigger than my beam size, that I'll have much sharper edges to my features than I do, for example, for these 1 micron features where I have some nice taper to the features I'm going to make that are, I guess, 3 microns wide here, because I made it 15 microns for 5 features. We'll see that they are much less taper. And I suspect we'll also see that you can see some bumps in the corners of the features, because I now am maybe not milling enough between the features. I'm actually not 100% sure we'll see that, but that's my guess, is that we will see that, and we'll know in approximately a minute if that's what happens. And again, while I'm doing this, for this particular, for bitmaps, my only options for scan directions are left to right, bottom to top. I don't have the full control over things like if I wanted to do spirals. So if I do care to do something like spirals, I usually do stream files, which I will show in a minute. I guess the other thing we can get started while we're still waiting is I'd like to show you guys drift control because it's amazing. So if you come to the programs, FEI, applications, drift control. If you click there, it will bring up a window. This guy, I like to put him down here. And what this will allow us to do is to track a feature and then use that to correct any drift that's happening. I'll show you that in a second, but let's come back to here because this just finished. All right, cool. Yay. Okay, so these are the features we just milled. And remember, they're much bigger compared to our beam size now. And you see, I got to zoom out even to see them. Some things you see, they're very flat tops. There's not a whole lot of taper to them. And also between the features, we now see this little bump because when I was doing smaller features, just counting on the fact that you're going to have this beam tail that's kind of patterning everywhere around the places that you're patterning, I was able to kind of ignore those corners. But this bitmap, if I did care to make features this big with this type of current, I would probably have to I'd have to edit the bitmap to have more milling in the corners. So I got rid of that little bump in the corner. The other option is I could just turn up the current. And by turning up the current, I'm making the beam larger. And therefore, I can make features that kind of look like the 1 micron features I made and just do it a little quicker and, kind of count on the smear that comes from the beam shape to get rid of those corners. So it's just important to keep in mind the interplay between your beam shape and your current and what bitmap you need to use to get to the feature shape that you want. All right, so while we have this, I want to show you guys the drift control. So I'm gonna come back over here. We'll take a look at what the FIB actually looks like. Now remember, I've got the FIB on right now. And that's fine, but while I have the FIB on, I am milling. So if you had a beautiful feature that you want to keep, you don't want to do what I'm doing right now because I am ruining my features. I'm milling away the features I just made. Now, right now, I don't care. These aren't features I'm trying to keep, but be aware when you are focusing, you are milling, you are getting rid of the features you've already made. So if I want to use drift control, I come to this menu that we got up from the start menu. I click setup. When I do that, it's going to create another box here and it's going to give me this info window, which basically says, find a feature you want to track, put it inside of this box. Oftentimes I like to track something like this, but beware if you have multiple things that look the same, sometimes it will be like, oh, I found it, it's over here. So you do want to be aware. So I'm actually going to let this one drift over to the next one so that it doesn't try to find the adjacent feature and track it. But whatever I put inside this box, the program is going to find that feature and make sure it's always in the same place. So once you've got that feature, you click OK. It gets rid of the box. It takes an image, sees what it looks like. If you come to defaults, this just says how often you want to take an image. So I'm going to say every 30 seconds. That works. It's going to take an image, recenter based on where this feature is. These are subtleties that you're welcome to change. Sometimes I change them. I wouldn't worry about them too much though. And then if I click start, it looks for that feature, it finds it, and it recenters. For something short like what we just did, it doesn't really matter. But sometimes I'm doing fibbing that takes, say, 2 hours to do the whole pattern. And in that 2 hours, I might have drifted a micron. And in drifting a micron, if my features are a micron, I've completely smeared them out. So drift control is great, especially for the really long patterns, because it makes sure that if there is any slow drift, it's being corrected for. And patterning is just the same if you're using a bitmap. So like if I wanted to go back and do our original pattern, I would just make the pattern. Again, it's 5 microns by 5 microns by 5 microns, and it's about a minute long. If I click go, it starts to pattern. It does everything just like it did before. It's just that every 30 seconds, it's gonna stop. It's gonna take an image. If anything's moved, it's going to recenter it, and then it's gonna keep milling. So there you go. You just saw it take the image, and it recentered, and it should do that again in approximately 30 more seconds. I also like this because you kind of get an update on how things are going along the way. Again, especially if you have like a 2-hour process going, you can, get an update every minute or so. So we'll let this finish. I do love drift control. As I mentioned in my presentation, drift control does not work well with stream files, which is what I'll show you next. So that is something to keep in mind. There are definitely advantages of stream files, but stream files don't work well with drift control. So it's kind of a bitmap thing. So once this finishes, I'll stop drift control. I'll show you the features, show you that they look essentially the same as they did before. All right, so stop drift control. Come over here, find our features. They look pretty much the same. If there had been a problem with drift, we should have corrected it, although we weren't having a problem with drift, so there's not much to correct at the moment. All right, the last thing I want to show you guys is an example of a stream file. To make a stream file, we click stream file, we make a little box, and I have a stream file which just draws a spiral. Now remember, as I zoomed in and zoomed out of my bitmap, it like zoomed in and zoomed out my bitmap, because I have in my bitmap, I could control like the X and Y dimensions of my bitmap. For my stream file literally just says, here is the pixel position. And as a result, I'll zoom in and zoom out. Oops, switch it to live. So I zoom out and I zoom in, and my stream file stays the same. So that's important to remember, that when you make a stream file, it's dependent on your magnification. So when I make a stream file with Python, one of the variables I input is this HFW, which is essentially the width of this horizontal field width. Thank you, Roberto. Is the horizontal field width. And as a result, I'm essentially telling it what the magnification is, so that it makes whatever feature I want to make the correct size and makes it in the right pixel position, if that makes sense. So I'm going to move over so we have a clean spot. And as I said, all this does is make a spiral. It's very quick, so I'm going to start it, but it's just going to happen really quickly. It's only 19 seconds total. But you should see, it's kind of slow to update, but you should probably see a spiral coming. Yeah, there we go. So it's happening. It's not updating in real time, but
it goes from inside out.
It goes inside out. And we should see when it's done. There we go. We should see. Okay, so I made a spiral of dots inside to out. I also, in this case, actually made it so it was very light in the middle and darker as I went out. So this is one method I use to make like nice, beautiful features, I guess, is to spiral around them. So this is an example of a single feature made that way. But yeah, if you want to do stream files, they give you a tremendous amount of flexibility over exactly where the beam goes and how long it stays at each point. But keep in mind that it also takes a lot of effort to make these, usually with MATLAB or Python or some type of script, because you have to put in thousands of points. And usually they're mathematically defined. So it's not something you want to do manually. But if you do have that, it's awesome. I will say that drift control does not work great with these. And the reason for it is if you start drift control and it starts doing its thing, say spiraling out, when drift control stops and tries to take its image to recenter, it will not automatically restart your your stream file. And if you manually restart it, it restarts it from the beginning. It does not restart it where it ended. So theoretically, this is fixable. However, it does not work currently on either this FIB or the plasma FIB. So currently, you cannot use drift control with stream files. You can use drift control with bitmaps. So I think that's all I wanted to show you guys. But I'd be happy to answer any other questions anyone has, or if anyone has questions in the long term, feel free to send me an email, or we can set up a Skype call or Skype, shows my age, a Zoom call, and we can chat about whatever problem anyone's having.